Well, good morning. This is 9:31 on a Monday morning, the 6th of February, 2017, Math 125, Calculus 1. One person came in and left, and I don't have anyone else in the class yet, but hopefully I think she will be back. She left her books and stuff here, so I'm pretty sure she will be here, but I don't know where the rest of you are. Hopefully you will be here as well. But that was Nicole, who is here. And today, by the way, like I said, was the 6th. All right. The only, I won't go into very much, but the only major announcement is if you are graduating this term, you've got to get your application and notification for graduation in this month. The sooner the better, okay? If you're graduating in the summer, this is a great time to do that as well. If you're graduating in the fall, planning to graduate in the fall, but are not coming this summer, then I would say go on and do fall as well, because if you're not going to be here in the summer, you have to remember at home to do it, and now you got someone reminding you, so I would say do it now. Okay, because we'll be registering for fall pretty soon, and you want to be certain that you know what you need to be taking. All right, that said, let's move on to where we left off. Again, I wish someone were in here, and I would see if you have any questions, but since no one's here, can't see that you have any questions. All right, let's get started where we left off last time, which I'm pretty sure was the beginning of section 2.5, evaluating limits algebraically. Okay? Now, I think this is exactly as you would expect it to be. Substitution can be used to evaluate limits when the function in question is known to be continuous. All right, good deal. You're the only one here. And just make sure you are Nicole, right? Yeah, do that, but make sure I put the right person down for the right thing. Now, we're now, I think I told you before, up to 5 students. But I've seen one of them out in the hall during other times of the day, but I haven't seen him here in this class yet. He hasn't been yet, so hopefully he is going to be coming. The others hopefully will be coming in too. All right, what we're talking about, are there any questions before I get started on today? Okay. Last time we finished 2.4, and I think just barely got our whatever they call it, preliminary questions done, and we ran out of time. So we're starting 2.5 today. And again, when you're evaluating limits, if the function is a continuous function, known to be a continuous function, plug it in, substitute. That's all you have to do, okay? However, if you have a function that has a discontinuity, you know it has a discontinuity, but you know where that discontinuity is, and you're at some other place, plug it in. That's all you have to do. Now, this isn't the graph that's here yet. This is one coming up, but let me go on and do the first couple. They're not formally examples, but they just show you. For instance, this. Let me get my pen. Okay. All right. I'm sorry? 2.5, yeah, page 84 or thereabouts. For instance, if you had this function, let's limit. The limit as x approaches 3 of x to the minus 2, what would that be? Now, I know automatically that x is not defined at x equals 0. But see, we're not evaluating it there. We're evaluating x equals 3. So what would you have? 1/9, exactly. x to the minus 2 is the same as 1 over x squared, so that would be 1 over 3 squared, which is 9. 1, 9. No question about it, no problem. Plug it in, plug it in. If that were x equals 0, none. There is no limit as x is approaching 0. Okay, so now the next example is then the one we have here. So now I'll go back and zoom again. I'll try to zoom again. There we go. All right, here's this one. Consider this limit. The limit, oh, it's not quite the limit. Yeah, okay. So what I'm going to do is shrink back again. All right, let me clear the writing there, and we'll do this one. The limit as x approaches 4 of x squared minus 16 over x minus 4. Okay? Does that limit exist?
It does, but x can't be. The answer would be x plus 4, right? Because you factor out the top.
You what?
Because you're factoring out the top.
Okay, you're absolutely right. Okay, if you look at this one, like we looked at the last one, here is a problem, Houston. When x is approaching 4, that denominator is approaching 0. And if that were it, if that numerator were 1 or 16 or minus 3 or 85 thirds or whatever, and the denominator was x minus 4, that would not exist at all. Okay? But that's because you have the 0 in the denominator with something else in the numerator. But on this one, x approaching 4, the numerator would be 16 minus 16. That's 0 also. So that's what I call an indeterminate form, which means the limit may exist. It may not, but it may exist there, so you have to investigate to see. And you're absolutely right. What we do on that, algebraically, is to factor that numerator. How does it factor? How's the numerator factor? Ah, here comes the jock. Okay, Richard. Okay. All right. The denominator doesn't factor. It's x minus 4. This is not the first example, but it's the first illustration, you might say, in 2.5 on bottom page 84 or thereabouts. Okay? And Nicole had suggested we factor the numerator. How does that factor? X plus 4 times x minus 4. There we breathe a big sigh of relief because we see we can now divide out the x minus 4. So now we can take the limit as x approaches 4 of x plus 4, and what would that be? That would be 8. The limit would be 8. Okay? Because 4 plus 4 is 8. We can now plug it in. However, if we were then to graph this function, obviously it graphs as the line x plus 4. Y-intercept of 4, the slope of plus 1. Okay? But, because the original function had a 0 in the denominator, x equals 4, that you can't evaluate. So that's where you leave a hole in the function. Okay? And the rest of the straight line extends for infinitely this way and that way. So they just stopped it at 0 to 8. But it extends indefinitely in both directions But it has no value at x equal 4 because you cannot evaluate it at x equal 4. Otherwise, it's a straight line. This is a discontinuity. What type of discontinuity is that? Removable, because you could plug in and say, let it be this for all values except x equal 4, and let it be, say, 8 at x equal 4, and now you've got a, then you could color that line in and not have the open circle anymore. Okay? So that is a removable discontinuity. The limit does exist. Okay. Now, there is a block in the middle of the page. Both of you have your books, don't you? I don't know about the rest of the students, so I hope they have theirs by now. I can't recall that they all do. I think they do. Okay? So I'm just going to refer to the top part of page 85. We say that f of x, and this is what I've been harping on all along, has an indeterminate form or is indeterminate at x equals c if the formula for f of c yields an undefined expression of the type 0 over 0, or infinity over infinity, or infinity times 0. Boy, who wins on that one? We don't know. Or infinity minus infinity. Who wins on that one? We don't know. Okay? So if it has one of those, what's that, 4 forms, then, no, 5 forms. 1, 2, 3, no, 4 forms, sorry. Then we call it an indeterminate form. If it's 1 over 0 or any fixed number over 0, that's undefined, and you know the limit will not exist. One of these forms, you don't know if the limit exists or not, and that's where you investigate further. Indeterminate forms are warning signs that tell us more work needs to be done to evaluate the limit. Our strategy when this occurs is to transform f of x algebraically, if possible, like we just did on the previous example, into a new expression that is defined and continuous to x equals c, then evaluate the limit by substitution, plugging it in like late. Okay? As you study the following examples, notice the critical step is to, they say, cancel a common factor. Divide out a common factor from the numerator and denominator at the appropriate moment, thereby removing the indeterminacy, if it's doable. So here's the next one. The limit as x approaches 3 of x squared minus 4x plus 3 over x squared plus x minus 12. I'm going to blow this up. Let's see. I think I won't do that yet. Let me write this in. The limit as x approaches 3 of this thing. Okay? All right. Now I'll blow that part up as much as I can. Okay? Forget what you see to the right. What we're trying to do is this. Well, first thing I always do, try plugging it in. The place that's going to give us problems would be the denominator. Plug it in here. 9 is minus 12 is 0. Problem. Okay. Now, don't lose hope until you also plug in the numerator as well. And that would be
9 minus 12
would be
3, or positive 3 plus 3, 6. Or
okay,
excuse
so
me, negative 3.
9 minus 12 is negative 3 plus
Yeah,
3 is 0.
sorry.
If that had turned out a 6, hang it up, Jack. You can't take the limit. The limit doesn't exist. But since that does come out to be 0, that's an indeterminate form, so now we investigate further. And what we do to investigate further is see if we can factor this and factor that. Does this factor? Don't look. How would you factor that?
Let's see, x minus 3, x plus 1. Right? Is that right?
Okay.
No.
Your x's and x's are right.
Yeah.
But because this is a plus,
Plus,
both
they're
of those
not
have to be the
negative.
same, they both have to be negative.
That's right.
So x minus 3 times x minus 1. Sure enough, that works. How about the bottom?
And then x plus 4, x minus 3.
Yes, and notice there you have x minus 3 numerator and denominator. They can go out because they've been dating. And then what you have is x minus 1 over x plus 4. Now we can evaluate that limit, and that would be what?
2 over 7.
2 7. So that would be the limit. Now, at x equals 3, you have a hole in the graph, okay? Okay? The rest of that would plot to be a rational, that would be a rational function, okay? You have a vertical asymptote at x equals -4, right? Because you can't do that. And you have a horizontal asymptote at x equals 1, the ratio of the leading coefficients there. I hope you remember this from last one as well. So there you have your x, and then it does something here and something down here. So except x equals 3, you have a hole in the graph. But it would be a removable discontinuity. Okay? So let's watch and see how they do it. They divided out the common factors, x minus 3, leaving x minus 1 over x plus 4, and continuous at x equals 3. So plug it in, plug it in. But remember, x still can't be equal to 3, but it's continuous there. That's not, the second part is continuous there. It's the whole function, though it's not, but it's a removable discontinuity there. I think that's all she wrote there. So our answer is, as we have just said, I don't think they show this. Let me, do they? No, this is a different problem. Okay. The answer is 2 7, as you already did in your head. All right. Any questions on that one? Okay. Next, we have to calculate this one. A very different problem. Let's just see. Yeah, I think we can do it on this one. Yeah, because that is the graph of it. Calculate the limit as x approaches pi halves of tangent x over secant x. Okay? Now, what would be your first inclination? Plug it in, plug it in. Okay, what's tangent of pi halves? Say again? It's a vertical asymptote. It's completely undefined there. How about secant of pi halves? Same thing. Completely undefined at x equals pi halves. So this is an infinity over infinity type discontinuity, not a 0 over 0. Well, what would you do? Hang it up? No! We never hang it up! Unless you've already watched it. Never mind. What do we do?
I guess try to transform it.
Okay, and how would you do that?
Write it sine over cosine.
Ah, very good. What we use our trig identities to simplify it is another way of saying that. And that would be, as you said, tangent is sine x over cosine x over
What's that? 1 over cosine?
1 over cosine x. And by the way, then I can, multiply those away by multiplying numerator and denominator by cosine x, because cosine x over cosine x is 1. That would eliminate that, and this would be then the limit as x approaches pi halves of sine x over 1. And what is that? 1. No, 1. Cosine there would be 0, but sine would be 1. Okay? Now, what they did here was plot the two of these, and you see that sure enough, as x approaches pi halves from the left-hand side anyway, from the lower side, both tan x and secant x are going to infinity. positive infinity over positive infinity. Coming from this way, they were approaching negative infinity. But again, negative infinity over negative infinity would be something, just infinity, because the quotient would be positive. So who wins or loses? And how do we go from there? Okay? Well, by doing what y'all suggested, you do come up with a potential answer. And let's see, I don't think the book carries it any further. No, this is a different problem. Okay? So, sure enough, it comes out being 1. By simplifying just as you suggested, and that would be sine x. So, they did not graph this, okay? If that, yeah.
I didn't even think about that. How they rationalized it out was they did sine x times 1 over cosine x.
Right.
And then you could do, I don't know, I mean, it just looks a lot better if we say sine x over cosine x, but that is, I mean, it's the same thing.
Yeah, right.
Know?
Yeah, the way they did it, they divided out 1 over cosine over 1 over cosine. Right. What I did was multiply numerator and denominator by cosine.
Same thing.
It's the same thing, yeah. Okay. So they get the limit of 1. All right. I think this is not the next one, okay? The next one doesn't have a graph, so let's just do example 3 on the same page, but it just won't pertain to the graph at all. Evaluate this one. The limit as x approaches 4 of the square root of x minus 2 over x minus 4. All right. What would be your first inclination? Plug it in, okay, and what does that give you? Square root of 4? 2 minus 2 is? Okay, and the denominator? 0. That's an indeterminate form, 0 over 0. But what do you do with a problem like this? I'll tell you, it's a trick. It's a trick you use often enough, you can call it a method. Okay. Now, here's what I would. If that square root of x minus 2 would be in the denominator, then one thing you might say to do is rationalize the denominator. Okay? By, how do you do that? By the conjugate. Well, now, let's just rationalize the numerator and see what happens. Okay?
Putting everything in the denominator?
No. Well, it's just do it and see what happens. Okay? All right. So we're going to multiply the numerator by the square root of x plus 2. And if you do that, you also have to multiply the denominator by the square root of x plus 2. What's that? Yeah, it's going to the bottom. You move your problem to the bottom, except it's no longer a problem if you multiply the x plus 2. Okay, well, let's see. Let's multiply that top together and see what we get. What's the square root of x minus 2 times the square root of x plus 2? X what? I couldn't hear. Minus what? 4. Isn't it? All right. And your denominator is x minus 4. I can't write. Times the square root of x plus 2. And what happens here? The x minuses 4's go, divide away, and you're left with a 1 in the numerator, and what's your new denominator? Say again?
Okay, so it'd be 1 over 4.
1 over 4.
I was like, but that was whenever we had the minus 2. Cool.
Yeah.
Okay.
So you see, again, now you might have asked yourself, would it work to multiply by the conjugate of the denominator? You could try it and see, but you see it really doesn't help any because there's no factors to go out. The numerator does produce a factor you can't take out of the denominator. All right, so it has an answer of 1/4. All right, this next one doesn't have a graph or a slide on it, so let's just do that here too. Can I keep continuing in the same area? This is getting far closer to what we're going to be doing later, the limit. This time it says h is approaching 5, which is not really close to what we're going to do, of h minus 5. I look at that and say, I've got a 0 in the numerator already, but what do we have in the denominator? I'll lose it again. There it is. The square root of h plus 4 minus 3. The square root of h plus 4 minus 3, right? There it is.
3. Well, it's 9.
Yeah.
Square root of 9 is 3. Minus 3 is 0.
Yeah. So again, we have a 0 over 0 situation, indeterminate. And if that would have been 7 over 0, hang it up. It's not going to have a limit. But with a 0 over 0, it may or may not. We've got to investigate it further. How would you suggest we proceed with this one?
Would it be the same instance? Would we multiply by the conjugate?
That's the denominator, the one with the radical in it. Don't know if it's going to work, but that's, I think, your best shot. So multiply by the square root of h plus 4 plus 3, okay, over or under, ooh, too much, okay, the square root of h plus 4 plus 3. You have to multiply the numerator and denominator by the same thing. So what does this give you in the denominator?
Is that just h plus 4?
H plus 4
And then minus 9?
minus 9. Okay, in the numerator, h minus 5 times this ugly thing, the square root of h plus 4 plus 3.
Well,
Okay.
that doesn't work even on the denominator.
What's that?
It doesn't work on the denominator.
What doesn't?
Well, whatever comes back.
Okay, here we go.
Because that would be 5 plus 4, 9 minus 9.
H minus, there you go.
5 plus 4 is 9 minus 9.
Okay. Okay, but wait. Let's, yeah. What is that? H plus 4 minus 9 is H minus, combine like terms. Huh?
5.
Yes. And now?
Okay. All right.
Yes, it still works, all right?
I was like, no, but okay. Okay.
All right. And now what do we have?
So we just plug it back in. So that'd be 9, 3, so 6.
6. You got it. There it is.
Okay.
So that works too.
It didn't click. I was like, dang it, we're going to get a 0 on the bottom. But okay, cool.
Okay. All right. Now the next one we do have a slide for. Okay. Was there any questions on that? Sorry. Okay. We do have a slide for this one, I think, if it's the same one. Yeah. Really kind of messy, but it is the same. Okay. I'm not even sure it's worth blowing up. Okay, but let's see. The limit as x approaches 1 of 1 over x minus 1 minus 2 over x squared minus 1. Now, if this ended right there, what would it be?
It'd be 1 over 0.
Yeah, which is blows up. It's 1 to infinity. And then you say no solution. Does not exist. Now, if you had just that, or even that, what would you have?
That's 2 over 0.
Which would be Undefined. Both of those by themselves are undefined. But then the way they're looking at this is going to, especially if it's approaching x from the left-hand side, from the lower side, then this is approaching infinity, and this is also approaching infinity. No, I'm sorry, I said it backwards. That would be approaching, it's approaching from the left-hand side, that would be approaching negative infinity, and this would be approaching negative infinity. Okay? So negative infinity plus infinity. Okay? Or from the right-hand side, this would be approaching positive infinity, and this would be approaching positive infinity. So it would be infinity minus infinity. Okay? Still, those are indeterminate forms. Okay? Not because it's infinity or 0 over 0 or infinity over infinity like our first two examples were, but this is infinity minus infinity. Which infinity wins? We don't know. It could be if this was huge compared to that one, that may be going to infinity. If this one's huge compared to that one, then it may be going to negative infinity. Or if they're close enough to the same, it may actually go to 0 or something else. Okay? So, what could you do here to try to simplify this? What if the limit weren't there? What's that again?
If you can take a squared minus a squared plus 1
Okay, yeah. Let's find the least common denominator of these two denominators. And the first thing you do is factor here. X, what did you say it was? No, x plus 1 times x minus 1. It's already squared, but when you factor it, it becomes that. Okay? And this is just that. Okay? Well, I need, in order to subtract those, I need the least common denominator. What would that be? No, this thing.
Oh, okay, sorry.
So to get this one to have that same denominator, I would do x plus 1. But if I multiply down there, I have to multiply up here as well, because I can't be discriminatory, right? Okay. So what does that new numerator become? X plus 1 minus 2 over x plus 1 times x minus 1. Yeah. Okay. Right? You buy that? Okay. Are we lost? What might you do next?
Divide out the x plus 1s.
Can't do that.
Well, I guess because it's never mind.
The numerator becomes a x minus 1, combined like terms, right? The denominator is x plus 1 times x minus 1. And guess what? You can divide out those, leaving your 1 up here, and you have 1 over x plus 1. And you want to take the limit of that as x approaches 1, from whichever direction you want. And what does that give you? Okay, x plus 1 minus 2, combined like terms. X minus 1. Because you add the plus 1 and minus 2. Okay, so you like terms. Say that again. Okay, right, but you see, once you got it there, you can remove the parentheses, right? And here we have some area. Okay, got 3/5 of the class here now. Way to go! Increase the class size by 50%. Excellent. No, we just combine like terms. Sort of like he didn't want to do in the last problem, okay? It was in the denominator there. But the same thing here. X plus 1 minus 2 is just x minus 1. Combining those like terms. X minus 1 now divides out with x minus 1 in the denominator, leaving you that. And the limit as x approaches 1 there of 1 over x plus 1 would be, can you evaluate that one? 1 over 2, exactly. So this is 1/2. Now, I never would have imagined that an infinity minus infinity would wind up being 1/2. But it is, okay? They're close, awfully close to each other, but they're still 1/2 of a unit apart, which I mean, I don't even know how to describe this, except that as these are going up or down, let's see, the top line was your first one, 1 over x minus 1, okay? When x equals 0, that would be 1. The second one was 2, x equals 0 would be 2, okay? Minus 2. Now, as these are going down, this is strange to think of it this way, but it's what's happening. The blue line is going down, and you're subtracting the 2 a little bit slower than the red line is going down. And the difference between those is 1/2. I mean, that's bizarre, but it's true. And from the other side, the same thing. The blue line is leading. The pink line, yeah, I guess that's the, yeah. Blue line is leading the pink line by 1/2. As you get closer and closer to x equal 1, the blue line is just 1/2 ahead of the pink one. So the limit, either place, one is minus 1/2 over minus 1, whatever. Minus 1 over minus 2 is 1 minus a minus would be a plus, and the other is a plus 2. So you don't see that graphically, though. It's you do it algebraically. All right. That said, any questions? This was example 5, the top of page 87. You don't have a book yet? Okay. Say again? Okay. Do you want one to look at during class? Oh, I've got, Dr. Bryant's copy is back here, but he needs it tonight. Don't leave home with it. Okay, don't leave it. Yeah, I'm going to have that back for him. Top of page 87. Okay. And moving on to example 6. Okay. Let's take a look at this one. The limit as x is approaching 2 of x squared minus x plus 5 over x minus 2. What would you do first? Plug it in, is that what you said? Is that, I wasn't hearing well. Is that what you said? Okay, right. Okay, and what do you get? I'll do the denominator. 0? Okay.
Yeah.
All right.
And that's 4 minus 2, which is 6, plus, hold on. 4 minus 2, 2 plus 5, 7.
Okay, so your form would then be?
7 over 0.
Okay. And what?
Where
you stop right there. That is undefined, not indeterminate, undefined. You'll never find a limit for that. It can't exist. That's an undefined version. And here they show the example of that. you have a y-intercept here, and a y asymptote here, a vertical asymptote, I can't say, a vertical asymptote here, and actually here you have what they call a slant asymptote here. I don't know if you did this. I know I usually skip it in Math 100. We get to it in 112. So that is a slant asymptote there. And you just hang it up because there's no way it's going to negative infinity from the left, positive infinity from the right. Narrow the twain to be, they can't ever have a hope of meeting because there's no two functions that are getting close to each other or something else like that. One function getting further and further apart. No limit at all. Now, I think it's just saying the same thing we did, just in different words. I'm just making sure I shouldn't go back and repeat some of it in different words, but I think it's okay. All right, let's go to example 7. I don't think they have a graph here either, but I will erase all the ink, and let's do example 7. Let's calculate this one. The limit as h approaches 0 of h plus a squared minus a squared over h, where a is any old constant, is just a constant. H is kind of like the variable, but not quite. It's just what is approaching. So what would you do first? Because h is approaching 0.
You're going to have a problem with the denominator.
Yes, it's going to be 0. It's going to 0. Yeah. Now, if the numerator is going to 0, we have an indeterminate form. If it's not, we can hang it up and say there's no limit. Absolutely none. What is that numerator going to? When h goes to 0, what's left over in the first part?
A squared.
A squared minus a squared is 0. So that is an indeterminate form. Maybe there is hope. Let's see what that hope might be. Well, what would you suggest doing first?
Pulling it out.
Yes, exactly. Let's expand the h plus a squared. And what does that give you? H squared
plus AH, or
2ah. Remember?
Right.
When you pull it, yeah, you're going to have two cross terms. Add them together.
And then a squared.
Plus a squared. Then you got a minus a squared divided by h. Okay? Let's continue simplifying as long as we can.
A squares go.
Yes, they add to 0. So you can get rid of those. And then you have h squared plus 2ah over h. What can you do there?
Did you take out an h in the numerator?
Yes, factor out an h in the numerator. And that leaves you with an h
plus
2a and divide by h. And guess what you can do now? Divide out an h. Now we take the limit as h approaches 0 of h plus 2a. What would that be? 2a, you're right. Because as h gets closer and closer to 0, has less and less meaning, you're approaching 2a. Yes, that limit does exist, and it is 2a. Yes? You what?
If I do this at home,
you'll see everything that's projected with everything that's being said. Now, whether it can pick up some Maria's voice, she's pretty quiet, you know. But, and you're sort of far away. I don't think there's any hope that it can miss Richard. I mean, he's loud enough. No, I'm just sorry, kidding. No, actually, because the microphone's this way, it's probably mostly going to hear me. But you might hear some of the others too. But, yeah, you'll see everything that's there and hear it. Yeah. So you'll see all this just like we do. What you don't see is this. The pointing at things, you don't see that. That's not being projected, that's me pointing. So that's the part you have to use your imagination.
I think that'd be cool. It could pick up your shadow and show,
Yeah.
you know.
No, it doesn't do that. It picks up what's going to the box, not what's coming out of the box.
Yeah.
Okay, or what's hitting the board, not what hitting. All right, and there we have 2A. And we're going to see that one again, folks, I promise you. Okay. Now, in the next section, we'll use the squeeze theorem to evaluate that limit. And it can also be evaluated using L'Hopital's rule. And I don't know, do y'all remember L'Hopital's rule? Okay, we'll probably go over that, but that's next time. Let's look at preliminary questions first. Which of the following, let me just make sure there's no more slides. So what I'm going to do here is clear all that ink, and we'll ignore the picture or the figure and just go with the questions. Which of the following is indeterminate at x equal 1? X squared plus 1 over x minus 1. X squared minus 1 over x plus 2. X squared minus 1 over square root of x plus 3 minus 2, or x squared plus 1 over the square root of x plus 3 minus 2. Okay. Which of the following of those is indeterminate at x equal 1? The first one? The third one. Okay, first one is not?
First one's not. You get 1 over 0.
No, actually it's 2 over 0.
2 over 0.
2 over 0, that's undefined. Don't even try.
Right.
The second one you get?
You get 0 over 3.
Which is?
Undefined.
No.
Or is that not the?
It's 0.
0. Okay.
Numerator v 0 doesn't give you any problems at all unless the denominator is 0.
Right.
That denominator is not 0, that has a limit of 0.
Okay.
But it's not indeterminate. That's what the question
Okay.
is. Indeterminate is 0 over 0.
Right.
That would be 0 over 3, which is not indeterminate. It has a limit, is 0. Okay. The third one, that would be a 0 in the numerator and a
0 in the denominator.
because square root of 4.
4 and 2.
Okay. And then the fourth one?
You get 2 over square root of 4, 2, 0. So, 2 over 0.
2 over 0, and that's undefined, not indeterminate. So you're right. Only the third is indeterminate. The second one has a limit. They didn't ask that. They said, is it indeterminate? No, it's not. It's 0. Okay.
So
Now,
when the numerator is 0 and the denominator is a number,
yeah,
you'll have a limit of
0.
whatever, 0.
Yeah.
Okay.
Whatever that numerator is.
Cool.
I mean, because it's 0. Okay. It's only when the numerator and the denominator is 0, numerator and the denominator infinite, it's a infinity minus infinity. What was the other one? There was one more.
0 over 0.
Infinity times 0.
Yeah.
We don't know who wins or loses there. All right, let's go to number 2. Give counterexamples to show that these statements are false.
Can I tell you something a little funny too?
Yeah.
What's worse is all that is like just a little bit over the preliminary question. What we were just looking for.
Right.
It's right there underneath.
Oh,
the
yeah, right
summary.
there. Right. I flip back the pages. It's right there. Okay, you're right. The summary, and that's actually one of the things I think Miss Martin liked best about this text, that summary there at the end of each chapter. All right. Let's see, hit the wrong button there. Let's clear the ink. And we'll go to example 2. Give counterexamples to show that these statements are false. So the assumption here from how they read it is that they're all false. If f of c is indeterminate, that's indeterminate, okay, then the right-hand and left-hand limits of as x approaches c are not equal. X approaches c, not equal. Okay, lots of abbreviation there. So if f of c is indeterminate, if that function is an indeterminate form, does that imply that the right and left limits at x equals c, ugly writing, as x approaches c, that's not equal, as x approaches c are not equal? It says, give a counterexample if that's false. One of the first examples we had was this one, x squared minus 1 over x minus 1. Okay, that definitely at x equal 1, that's indeterminate.
Right.
But at x equal 1, the left-hand limit, the right-hand limit are the same.
Right.
Okay.
So
yeah, that doesn't, just because they're indeterminate doesn't imply left-hand limits and right-hand limits as x approaches c are not equal. This one, they were equal. Okay? All right.
So would it be that if FC is indeterminate, then or basically it doesn't happen all the time? Is there?
Okay. If you're trying to reword that so it's true, is that what you're trying to do?
Exactly.
If f of c is indeterminate and the right-hand and left-hand limits are, as x approaches c, are not equal, then the limit doesn't exist.
Okay.
Yeah. But we know that some limits exist, so therefore the left and right-hand limits must be equal. Okay, the B one here. And I haven't been looking in the back just to make sure I'm giving you the same answers to the back of the book. This is 2.5 preliminary questions. Okay. The first one, they didn't list A, B, C, or D, but they listed the third one. Yes, same as we did. And then, yeah, they gave exactly the same example I did. F of x equals x squared minus 1 over x minus 1. Okay. Let's see what the B one calls for. If the limit as x approaches c of f of x exists, that's the given, then, I've lost my place, there it is, f of c is not indeterminate. Okay? And I put it's not equal to indeterminate. You understand that to mean it's not indeterminate. Actually, that first example works here too.
Yeah.
The limit exists, but f of c at x equal 1, in that case, is indeterminate. So, no, that doesn't work either. Let's see if they use a different example in the back, or use the same one. Yeah, they use the same one again. They like that one. Okay. And then let's do the C one.
So it is, if the limit of x approaches c, f of x exists, then f of c is indeterminate? Is that how, I mean?
Not necessarily. I mean, it could be x plus 1.
I'm confused as to what they're really wanting. I know they're trying to get our brains to think about, but to me, it's just a bunch of jargon, and they're what are they expecting us to rewrite this as?
Okay.
It's kind of my thing.
You sort of said it right the first time. What they're trying to get you to do is get used to the logic of it.
Right.
If this is true, let's see what that one said. If the first statement is true, find the reason why the second one is not. Okay.
Right.
And this one, if the first statement is true, find an example that would contradict the second one being true. That says, yeah,
Cool.
yeah, and that one example works on both of those.
Cool.
Okay. The C one here, if f of x is undefined at x equals c, okay, that implies, they claim, then f of x has an indeterminate form at x equals z. Okay? If f of x is undefined at x equals c, then f of x has an indeterminate form at x equals c. What you think there? They're basically already telling you it's false. It said find a counterexample. By the way, that one won't work anymore. But you can modify it ever so slightly and make it so it would.
Would it be the example 2?
I doubt it, because that one,
No, that was.
I think that worked. I think the better example would be example 6.
Okay, yeah. That was where that's where we plugged in a bit more.
Okay.
But
Here's I think an even easier one. 1 over x minus 1.
okay.
Okay, that is undefined at x equals 0. X equals 1, right?
Right.
Does that mean it's indeterminate? No.
Okay.
It's 1 over 0. That's not indeterminate.
Gotcha.
So this is undefined, meaning, now, technically that's undefined too, but that is beyond undefined, that's indeterminate. This side of undefined. This one is undefined and not indeterminate.
Right.
Okay.
Right. We
So
could
that's
have
what
used that example if it was x squared plus 1.
At the top of the...
Exactly. As long as there's a 0 in the denominator or the numerator at one point.
Okay, yeah, oh, you mean for this one?
Yeah, even
Yeah,
one, I'm
okay.
just saying,
Yeah, if you did a plus up there,
Mhm.
then that would be indeterminate here, but it wouldn't be, I mean, it would be undefined here, but not
But
indeterminate.
not
Right,
determined. Got it.
Yeah.
Cool.
Anytime you could have something other than 0 in the top, but a 0 in the bottom, that's undefined and not indeterminate.
Cool.
That one says it would be, but it's not. Okay. Now, example 3, or question 3. The method for evaluating limits discussed in this section is sometimes called simplify and plug in. Explain how it actually relies on the property of continuity. Okay? Well, basically, the property of continuity involves a limit. So, if the limit exists, then it's continuous. I mean, basically, that almost says it right there. but I bet you that's not adequate for them. Let's see what they're fishing for here. That last one, 2.5, they just said 1 over x. I did 1 over x plus 1, minus 1. So yeah. Okay. The simplify and plug in strategy is based on simplifying a function that is indeterminate to a continuous function. Once the simplification has been made, the limit of the remaining continuous function is obtained by evaluation. So basically, what they're saying here is the simplify and plug in is trying to get to a form that is continuous. If you can do that, then plugging in works. But all right, homework exercises there. Do 1 or 3, or both if you choose. Do any of the odds 5 through 33. Try to do 35. They say you need a graphing utility to do that, but see if you can think through it. If it gets too bogged down and you don't have a graphing utility, then don't worry about it. And then do any of the odds 37 to 41. Sorry. Try to do 43. I think that's a real good one to do. And then any of the odds 45 to 53. Good deal. So let's now look, even though one of those examples was a trigonometric limit, let's see if, let's just focus on trigonometric limits. So we'll, all right, trying to get this to progress. It doesn't want to. Let's go to 2.6. Well, it's taking its sweet time, but hopefully it's going to come up one of these days. For some reason my head's clogging up. I wonder if it's the dampness outside. Well, sometimes when it gets stuck like this, it helps to do a Control-Alt-Delete, start Task Manager. It says everything's running properly, so let's end that and see if that then jogs it into being, it didn't work this time, did it? Still trembling away there. So I'm going to just try it one more time. Still get no results at all. There, hey, whoa. Had it, but I clicked too many times. Here. Ah! It comes up and then disappears. All right. I'll go back and do it this way. 2.6. It's having some real problems with 2.6. I don't know why. I may have to teach from no slides, which is a shame, because they sure help save time. What I think I'll do is shut that down. What in the world is this? Okay. Let's go back to this again. I'll go all the way from the beginning. Sorry, folks. Chapter 2. 2.6. There. Worked fine. I don't know. All right. Finally, we're back. In our study of the derivative, which we haven't quite gotten to yet, we will need to evaluate certain limits involving transcendental functions such as sine and cosine. The algebraic techniques from the previous section are often ineffective in such functions, and other tools are required. In this section, we'll discuss one such tool, the squeeze theorem. We'll use it to evaluate trigonometric limits needed in section 3.6, which is where we're going to go in the next chapter. Hopefully we'll get that far. Okay? So let's consider a function f of x, that is the pink function here. Red if you prefer red. I don't know. All right. That middle function there. There's your f of x. Now, they also show that f of x is undefined at a certain point, at x equals c. Okay? But the rest of f of x always stays between L of x and U of x. I wonder where they got those names. A lower function or an upper function? Okay. So f of x is always in between L of x and U of x. Okay? They're saying consider that function f to be trapped between these two functions, L for the lower bound and U for the upper bound, on some interval I, and that could be from wherever this value is here, something. I don't know what your scale is here, but say x equals 1 or 7 or 3/5 or whatever, up to here where x would be 10 or 15 or 85 or whatever. But in that interval, f of x is always in between the lower bound and the upper bound function. Okay. Now, sorry. Okay. Here's how you say what they're just saying there mathematically, just so you'll get used to. I gotta get my pen back. All right. The L of x, which is the lower function of x, is always less than or equal to f of x, which is less than or equal to u of x. Okay. I may have to go clear my head. I hate to do it. I'm just having more and more trouble breathing. And this is true for all x in the interval I. So if this is your interval I, okay, and x is in between there and that c is in between there, all in that interval I. All right. The squeeze theorem applies when f is not just trapped, but is also squeezed to a point. So this is not going to illustrate the squeeze theorem. This is the trap theorem, but it's not the squeeze theorem. And so frankly, I really don't know why they did this except just to give you an idea of what it is. But you see, if f of x had been going to here, but then this continuous into here, still everything here would be true. But that would not be continuous. F would be continuous. The 10 o'clock scholar. Okay, Rodney is here. Good deal. Okay. Well, our faithful four that have been here are all here. It's that one new guy we added that we haven't seen yet. I've seen him in the hall a couple of times, but not in class yet. Hopefully you'll get here. Okay. We're talking about 2.6 trigonometric limits, but haven't even mentioned anything trig yet. We're talking about the squeeze theorem. So the squeeze theorem is not just that it's trapped between two upper and lower value, but beyond that, it's squeezed. So by this we mean that for all, that's sort of the trap thing. Here's what we mean by the squeeze theorem. the first part is still the same, but the second part becomes this. The limit as x approaches c of the lower function L of x, okay, is equal to the limit as x approaches c of u of c. Okay? And this limit for both of those, since they're equal, they're going to call L, which is just the limit. All right. What that's saying, as x is approaching c, not just that u of x is always greater than f of x and L of x is always less than f of x. That just means that the function f is trapped between the two. But like I'm saying, if that limit didn't exist, then the squeeze theorem wouldn't work, because now you have the green function and the blue function are approaching that same value there and leaving, and that value, that is capital L, meaning the limit as you approach it from the upper side and from the lower side. If both of those exist and are the same values, then f of x has to have a limit there too. So this just shows it being trapped. The next slide shows it being squeezed, okay? See, your upper limit is still always greater than or equal to f of x. The lower limit is always less than or equal to f of x. But at x equals c, the upper limit is approaching the same limit as the lower limit, lower function. And if they are approaching the same value, and f is always in between them, it has no choice but to have the value they have. Okay? That would be the limit. X equal L. F of x equal L. Okay? That would be the limit, because the lower function and the upper function both have that L at x equals c. And if f is always in between those two, then f of x has to have that same limit. Okay, there's the visual, here's the written. All right, squeeze there. Assume that x is not equal to c in some upper interval containing c. Okay? But the lower function of x always less than or equal to the f, and f is always less than or equal to the upper function of x. And this is the other part. First part, that x is not equal to c, the lower function is always less than or equal to f, and upper function is always greater than or equal to f. And the limit as x approaches c of that lower function, L of x, and of the upper function, u of x, as x is approaching c, both of those are approaching the same value, L, then it is left with the limit as x approaches c of f of x does exist, and that limit is also that L. Even though f of x may not be defined at x equals c, because we're not even saying that x equals c exists. We're assuming that it doesn't equal c. But that the limits of both the upper and lower do exist at L, and therefore by the squeeze theorem, since f is always in between those, it must be L too. All right, now, in one hand, that's so intuitively obvious, but they make such a big deal about it. Let's do this one, okay? Let's blow it up to start with, and if I write on it, it's going to have to shrink back down. But here's a function. Sorry. I may have to go clear. I hope not. Show that the limit as x approaches 0 of x sine 1 over x is equal to 0. Okay? Now, here is one way to look at this. I'm not saying this always gives you the right answer, but it's one way to look at it. Okay. I think, as we've already talked about several times in earlier sections, this limit, sine of 1 over x is approaching 0, does not exist. Because 1 over x is getting closer and closer to 0, the x's are staying, the function staying between plus or minus 1 because it's a sine function, but it's just going up and down, up and down, up and down, up and down, and never ever will the plane meet, because 1 over x is an undefined form, and that's just going to positive infinity, and sine, as you go to positive infinity, just keeps doing the same thing. It always has and always will do, going back and forth between plus or minus 1 ad infinitum. So, and is that, there is no limit to that. However, if you also put this function in there, x times that, well, we know what this function is. Y is equal to f of x. Y is equal to x. That's your identity function. Okay, whatever x value, y value, x value you have the same y. Okay, that's it's the main diagonal. Okay, however, okay, for if you then also allow y is equal to minus absolute value of x, then that's your anti-diagonal. That's that one. Okay. Well, I'm sorry. Minus x. I'm sorry. That's what I meant to say. Y is equal to minus x. It would be that diagonal. Now they go about putting in the absolute value signs here, which is okay to do too. You get the same thing. When you do absolute value, you get the upper v and the lower v. When you do the two diagonals, x and minus x, you get the same two functions. Okay. So basically what this is saying is that when x is a positive number, then it stays less than this value here. When x is negative, sine, remember, is always between plus or minus 1. Okay, I probably said that. Let's back up a little. Let's take x equal positive. Well, sine of 1 over x is either plus or minus. Okay? If it's plus, then you're up here. If it's minus, then you're down here, but you can't ever get below here. So that's why they introduced the minus sign, minus absolute value of x there. In other words, this function, as x gets closer and closer to 0, this factor is getting closer to 0. This factor is staying between plus or minus 1. The 0 wins. Okay? It shrinks it down and keeps it. Here's how I like to look at it, and this may not be fair. Remember when you did, or whoever you had for it, graphs of sine function. Okay? The letter or number that came in front was called the amplitude, or at least the absolute value of that was the amplitude. Okay? Actually, that works very well here. Which means whatever that was, that either blew up if the x were large, or shrunk it if it was small, meaning greater than 1 or less than 1. Because this thing's always between plus or minus 1. So for a large x greater than 1, that would mean between plus or minus 8. If it was less than 1, then it's between plus or minus 8 here. Well, so this is a variable amplitude, which means the sine function, that was going between plus or minus 1 is now going between plus and minus x. And that's why When it's plus x, it's up here, minus x is down here. So it's going back and forth between plus and minus x is over here, okay? And then the when x is positive and sign is negative, then your function value is down here somewhere. Plus times minus will be minus. When both of them are plus, it's going to be up here. When x is minus and sign is negative, then it's going to be up here. And when x is minus and sign is positive, the function is going to be here. So it's going to stay between your plus or minus, your amplitude, plus or minus x. So therefore, it does narrow down and go to 0. At least it looks like it does here. And indeed, that's the case. Okay? So, this is talking about it graphically. How to use the squeeze theorem to actually prove that. That's the next thing that they're going to do here, I think. Yeah. And I'm pretty sure, yeah. Okay. So let's do it here. As I already said, from this graph here, this function here is a product of two functions, the identity function and the sine function, okay? We cannot use the product law because the limit of 1 over x does not exist as x approaches 0. However, the sine function takes on value between plus or minus 1, and therefore, and here's how we're going to do this, or how they do it. The absolute value of sine 1 over x, okay? Sine 1 over x is that thing that goes back and forth, but always stays between plus or minus 1. So the absolute value of 1 over x is always between 0 and 1, okay? Now, it's just not defined for x equals 0. Okay, so we won't go there yet, but everywhere else it stays between plus 0 and 1. Okay. Now, if you multiply both sides of this equation, or all three sides of this inequality, by absolute value of x, okay? Well, they cheat a little bit, and there's a reason for it. They don't even say this thing. Let's just keep it the way they were saying. The absolute value for that is less than 1. Got to be. Sine stays between, or less than or equal to 1. It could be equal to 1. Okay? Just the x is not equal to 0. You can't have a sign of infinity. I mean, just don't even try it. Okay? Now, what they're going to do is multiply both sides of the inequality here by absolute value x. That'd be 1 times absolute value x. What does that mean? And this is where they get to the graph here. That means absolute value x is either going to be plus x or minus absolute value of x will then be less than or equal to absolute value of x times absolute value of sine x, sine 1 over x. That's less than or equal to, absolute value of x. Okay, it was a 1, I multiplied by absolute value of x. All right, basically you've got it knocked down, okay? This thing in the middle is basically the function that we're interested in, okay? Just lose the absolute value bars, and that's exactly the function we're interested in. But if you lose the absolute value bars, it's still going to be between plus or minus absolute value x, okay? And sure enough, because this has a limit of 0 as x goes to 0. That has a limit of 0 as x goes to 0. Even though this isn't defined when x is approaching 0, since you know it's between these two, the squeeze theorem, it has to have the same limit. And that limit of this is 0, that's 0, so that has to be 0. Okay. That basically is how they use the squeeze theorem. All right. Now, that leads to two really important trig theorems. Okay. And I can't recall now if they prove these. I don't think they do. I think they've already shown this in an earlier section. I just don't remember which section it was. It was earlier in chapter 2. Okay. The limit as theta approaches 0 of sine theta over theta is 1. Okay? Now, obviously this is an indeterminate form. As theta approaches 0, sine theta is approaching 0, theta is approaching 0. But we don't have any algebraic way we can prove that. Okay? None of those other techniques we use will work on this one because it's a transcendental function, a sine function. But we did show it. We did prove it earlier. And they show the graph of it again, and I'll get that in a minute. But that is equal to 1. We'll come back to that in a second.
That was the squeeze theorem?
We use the squeeze theorem to use it. Yeah. Okay. The limit as theta approaches 0 of 1 minus cosine theta over theta. This goes to 0. This goes to 1, that goes to 0. This is indeterminate form, that being 0 over 0. But that limit is 0, not 1. Okay? Now, you might ask yourself, why do they go to different values? And I can kind of give you a arm-waving explanation of it, but let's look at the graph, and you'll see they don't show the graph. Shame on them. Yeah. It's there in your book. This is the first one there. Okay. Okay, now, sine theta over theta, and we've shown this before. We know, okay, here they do a Holland function here, okay. This line up here, if I could draw straight, this is y is equal to 1, okay. Your sine function is 0 here, minus 1 here, 0 here, plus 1 here, 0 here, minus 1 there, 0 here, plus 1 there. So, no, I missed it. Okay. I messed that up really badly. I was doing the second one, not the first one. Okay, sorry. I wish they showed the picture. I wouldn't have to reproduce it here. The sine theta over theta, that's what they show here, is 1 here and goes to 0 at pi and at minus pi.
Did they really not include that?
Huh?
Did they really not include the picture?
On the slides, no, they did.
Really?
Okay. Well, you see, in the book, you see it doesn't have a Well, it does say figure 4, doesn't it?
Yeah. That's why I was asking.
I know. There's figure 3. There's the theorem.
Wow.
There it is.
Uh-huh.
Way over there.
Wow.
I can't believe it. Okay, there it is. Okay, so I don't have to draw it.
I just hated that you had. I was that would have been frustrating, you know.
Yeah, it was. But why in the world it's way over there, I don't know.
It's crazy.
Here's figure 4. Okay. Now, they showed this in an earlier section that the limit is sine theta over theta. It goes, that's the peak curve here. Okay. Now, I don't know if this would have been helpful or not, but I'm going to throw it in here. But of course, if I do it, it shrinks. Okay. Yeah, let's just go and use a pen. Okay. Here is, why is it, I can't get the pen, there, okay. Here is sine theta. At 0 at 0, at pi halves, it would be pi halves. So pi halves is, pi is 3.14, so pi halves would be about 1.5. So it's somewhere about up there. So there it would be, and something like that. There, this would be. So here would be approximately y is equal to x. Okay? Now, give me a color. They've used green, red, and blue.
How about kind of that dark purple right next to the color you already have highlighted?
Okay, this one right here. Okay. Yeah, that is a light purple.
Light purple,
Yeah, this is the dark blue. I didn't know that was blue. Okay, yeah, this is purple then. Okay.
I don't think you have it selected.
Okay. Here's what it does. Sine is 0 here, 1 at pi halves, 0 at pi, and then it goes on. This is minus 1 at pi halves, 0 here, and goes on. Okay, so there's approximately the sine function. Okay, now this is, I can't tell the difference. Can you?
I was trying to tell you didn't have it selected.
Okay. Yeah, I didn't, did I? So let's go back and erase. Okay, I'll erase those and draw them back in the purple I want them to be. Okay. All right, I left that one. It's 0 here, plus 1 here, 0 here, minus 1 here, 0 here. Okay, that's what the sine looks like basically. Now, what sine theta over theta is this thing divided by that thing. Well, they're almost the same values in here, right? So this over this is going to be close to 1. But then the sine theta starts decreasing here, increasing here. So basically, they deviate from that, and so they become less than 1. This is a negative value here, so it's still close to 1, but now the ratio is less than 1 because the numerator is less absolute value than the denominator. So sure enough, that's how the implied as it is. But the cosine function, here's the cosine, the light blue line, here's 1. 1 minus that, as you get closer and closer to each other, their differences are equal to 0. So sine theta over 0 is approaching 1, not equal to 1 because it's not defined there, but the cosine, sure enough, is 0 because it's the difference. It's 1 minus cosine. Yeah. 1 minus cosine is 0. So with those pictures in mind, and not a formal proof, they did that sort of earlier. Well, we'll come back and sort of do it here. These are 2 limits like this, and I will gladly erase that ink because we found it finally. Thanks for finding it. Okay. These are 2 really important limits to keep up with in trig functions. As theta approaches 0, even though that's the indeterminate form, that's approaching 1 sine theta over theta, but 1 minus cosine theta over theta, even though that's indeterminate, that's approaching 0, because those 2 are so close. The other 2 are also very close, but their ratios are 1. Okay, and that is a ratio, or approaching 1. Okay, now, that's theorem 2. That's where the picture should go. Now we're on to theorem 3. And this is what they're going to use to prove the second part of theorem 2, I think. Cosine theta is always less than or equal to sine theta over theta is less than or equal to 1 for minus pi halves to pi halves. Okay? Now, let's jump ahead again, and I'm going to, on the graph, write those entities down. Okay? So what I'm going to do is lose the ink that we had here. That was to show why that ratio was close to 1. Okay? So with that being the case, notice what it says, that cosine, let's go back to my dark purple or dark blue or whatever it is. Okay. Cosine theta less than or equal to sine theta over theta less than or equal to 1. If I can breathe for another 2 minutes, we'll be through, I think. All right. The graph is showing this. Not forever, but for all the points of interest. Here's the cosine curve, right? Y is equal to cosine theta. Here's sine theta over theta, okay? And here's y is equal to 1, okay? Now, this is not good forever because somewhere out here, before you get to minus 3/2 pi, this continues going down, that continues coming up. But everywhere, certainly between minus pi and pi, this inequality holds, for sure, okay? Now, since that's true, that cosine theta is always less than sine theta over theta, and that's always less than y is equal to 1, certainly between minus pi and pi, probably you can get a little broader, but who cares? We're only interested near theta equals 0. Near theta equals 0, that's going to 1, that's always 1, therefore this one has to be 1. Squeeze there. Not defined, the pink is not defined right there. The blue is and the green is, but the pink has to have that same limit because it's always between these two, including there, and those have the same value there, therefore this one has the same value. Now, squeeze theorem gives it to you just like that. Trying to see what they're trying to prove here. Okay. See if I can zoom in on these. I believe I can. Okay. Now, in the first quadrant, which is between 0 and pi halves, okay, the area of this triangle here, the one that's colored in here, and this is a unit circle, radius 1. So the area of this triangle here is 1/2 the base, which is 1, times the height, which is every point on the unit circle, the coordinates are, especially in the first quadrant, or everywhere really, cosine theta for the x, y, z, and sine theta, right? So therefore the height here is y, sine theta. The base here is 1. So 1/2 the base times cosine, times sine theta. That's equal to the area of the triangle inside there. Now, the sector right there, the area of that sector, is 1/2 theta r squared. I don't know if you remember that, but r is 1, so that is 1/2 theta, because r is 1. And it's pretty obvious to me that this is less than that. This area of this triangle has to be less than the area of the sector. But let's go beyond that to the triangle that superscribes that. In other words, make this your adjacent side. This is your opposite side. That's going to be tangent theta for the same theta all along here. Your opposite side is now tangent theta, okay? And your hypotenuse has changed too because it's a difference there. But obviously that triangle has a much larger area, 1/2 r times the tangent of theta, okay? And your theta is, I can't remember what they said before, but it's certainly if theta is less than pi fourths, the tangent of theta is going to, if theta is greater than pi fourths, certainly that area has got to be greater than the other two. So that gives us 3 areas that less, middle, greater. Okay. Now, yuck. Where do the H's come from? Oh, this is example 2. It's jumped another rabbit. Okay, so this organization of the book is rather strange because now they moved to proof of theorem 2 after they've done this other part that was proving theorem 3. So anyway, and we're out of time. Sorry, aren't we? Y'all let me go over. But guess what? I'll not charge you anymore. Okay? So we'll stop there and pick up next time. What's the next slide? Oh, this is example 2. So we'll just leave example, that proof alone. You can read it. If you have any questions about it, by all means ask and we'll go over that. But this is example 2. And we'll pick up and go from here. And we've just got example 2 and 3 to go, and we are almost through with this section. So homework exercises here. Do number 1 and or 3. I'll say any of the odds 1 through 5. You choose. Try doing any of the odds 7 through 15. I think we'll stop there and we'll pick up the rest of those next time. All right, good deal. Okay, and this is my morning class. I have 4 students in it. 2 of them I see right after lunch, 2 of them I see the last period of the day. This class, I don't have any of you anymore. No, yeah, I don't have Rodney anymore. It's bizarre. In these first 4 classes, I have 3 Williamses. Marcus Williams, Rodney Williams, and Nigel Williams.
Oh, yeah.
I have 2 of the 3 in 2 classes each, and the third one, Rodney, only in 1 class. I can't tell who's on first. Anyway, we'll end it there.
Thank you. I'll see you Wednesday.
Okay.